Good morning, everyone. This is Mr. Couple. Today I'm here with my IBSL Year 2 students. We'll be learning about renewable power production. If you're on the voice chat, you should say hi right now.
Hello.
Hello.
We got Joel and Cassandra. Good to see you guys here. So there's three main ideas for today. We're going to be talking about solar power, we'll be talking about hydroelectric power, and we'll be talking about wind power. And we're going to do calculations, mathematical calculations for all three of these energy sources, just to kind of get an idea of how they compare, advantages, disadvantages, and things like that of these renewable sources. All right, let's begin. So the first thing I want to talk about is something I didn't actually know about until I started teaching IB, was that there's actually two different types of solar panels. So when someone says solar panels, they could actually mean one of two different things. And in fact, when IB Physics says the word solar panel, they don't mean what we think of in America. So there are actually two types of solar panels. So do you guys know what these two types are?
I mean, I recognize the ones on the left just because
Mhm.
I've seen them before, but I don't really know what the ones on the right are.
Yep. So the ones on the right were more, they don't really use them too much anymore. They were mainly used back in like the 70s or so, like here in America, but around the world, they use these all the time. They're just in America, we don't use them so much. So I'm going to delete these and show you guys what they are. So these are called photovoltaic modules, or PV, and then these are called solar heating panels. So the two types of solar panels are either you can generate electricity. So over here, we're going to make electricity. And over here, you're going to make heat. So those are the two types. So you can either take the solar energy and convert it into electricity, or take the solar energy and convert it into heat. So that's when we say solar panel, you need to make sure that you realize that there's actually two types and don't confuse them from each other, because they're completely different from each other. So here's my little explanation of both of these types of solar panels. So we'll look at the photovoltaic modules first. So the way photovoltaic modules work is the sunlight comes in. So here's the sunlight comes in and it hits this semiconducting, or we call it a crystalline semiconductor. It's usually just silicon. And so the sunlight will hit that, and what will happen is it will liberate electrons from the conductor, like from the semiconductor, from the silicon. So like electrons will get removed from the atoms, and then those electrons start to flow around, and they create a potential difference, and then that enables electricity to flow. So you end up getting a potential difference across the two sides of this semiconductor. So where the top side becomes negatively charged, the bottom side becomes positively charged, and so you got this potential difference. So current is going to flow through that wire, and then create electricity, light up light bulbs. With a solar heating panel, what happens is you have the sunlight coming in, and then what you have is you have basically a device. It's usually like a little box. Like I'll draw a picture over here. There's like a box, and then you have like a pipe that comes in, and the pipe just kind of like wraps around a bunch of times, and then you have a pipe that comes out, and then you just shine the sunlight onto that, and it'll heat up the water that's flowing in those pipes. Then you just redirect that pipe, the flow. So once the water comes up here into the panel, it gets heated up from exposure to the sunlight, and then now that hot water then gets pumped back down into a storage tank. Now, this isn't going to be your like only source of heat. Like you would be taking cold showers most of the year, but it can help supplement a traditional boiler, like a traditional water boiler, like you would have either be an electric or gas powered boiler. And then you just take that hot water and add it into the mix. And then the idea is like that would slowly, like subtly or slightly lower your heating bill and kind of be more efficient, since you're getting the energy from the sun rather than having to burn a fossil fuel for it. So that's the gist of the two types of solar panels. Do you guys have any questions about, or like what questions do you have for me about solar panels?
Are the solar heating panels just like less efficient? Is that why we stopped using them?
Yeah, I mean, I don't really know why they just kind of fell out of fashion. They are pretty expensive to put in, and it's kind of like, well, why would I spend all this money to put in the solar heating system when I could just burn gas? And so people just kind of fell out of favor in the U.S. I'm not really sure. That'd be a good thing to research. But yeah. Okay, let's talk about some calculations that we can do for solar. So one of the most important things to realize about solar power is that you're getting the energy from the sun. And so the sun has these fusion reactions that are just releasing a tremendous amount of energy. It's like the amount of energy that the sun releases in 1 second is more energy than humans have used in all of human civilization. So the sun is just dumping out tons and tons of energy. But the thing is that not all that energy obviously is going to reach the surface of the earth. So if you look at this picture, so what happens is if you're in the upper atmosphere, you get about 1,350 watts per square meter. So if you've got like an area that's 1 square meter, 1 meter by 1 meter, and you put that in the upper atmosphere, then that energy or the power that goes through that surface is about 1,350 watts or 1.35 kilowatts. So that's a pretty significant amount of energy. Now, the problem though is that when that goes through the atmosphere, we're going to have some absorption through the atmosphere, and not all that energy is going to make it to the surface. So by the time it gets down to the surface, it's only about a kilowatt. So you about a kilowatt per square meter for your solar efficiency. So you have to realize that's like the top of a Minecraft block, right? That's 1 meter by 1 meter. That's a pretty large area, and you're getting about 1,000 watts from that area. So if you have a say 100-watt light bulb, you could power 10 of them off of a solar panel that was that large, about 1 meter by 1 meter. The issue, so the intensity of sunlight in the upper atmosphere is about 1350, but then that gets reduced to about 1,000. Now that's the maximum because it actually varies based on latitude. I'll talk about that in a second. Time of year and weather effects. So clearly, if it's a cloudy day, you're not going to have 1,000 watts per square meter making it to the surface of the Earth. And then also, depending upon where you are on the Earth, you can get different amounts. So what we usually use for a global average is 245. So 245 watts per square meter for a global average. Let's talk more about those variations with latitude. So from the waves unit, we might remember this equation that the intensity is power divided by the area. So what we're going to look at is let's say that the gaps between two of these lines, let's say that's like a constant power P. So let's look at the light. This is the sun from the light from the sun coming on and hitting the earth. So here's the same amount of power in these two locations, but notice that here it's a very small amount of area on the earth that power reaches. Whereas in the second case, here like at the poles, it's a much larger area that the power is spread out across. So if you spread the power out, the same power spread out across the heck did I if you take the same power spread out across a larger area, then you're going to have a less intensity. So at the equator, you got that 1,000. I'm not going to use green, it looks kind of gross. At the equator, you have the 1,000 watts per square meter. But then when you get out to the poles or to the extremes, the intensity is going to drop. So that's your intensity at the equator, but out here you're going to get lower intensities. And the reason is because the sunlight is being spread out over a larger area just because of the angle that it hits the earth at. So now why is this important? Well, because the seasons can change this. So depending on the different time of the year, the tilt of the earth is going to be different as it faces the sun. So over here, this is during the winter in the northern hemisphere. You can see that if we're up here, like we're there on the Earth, roughly that spot where the United States is. So you can see that the tilt of the Earth is causing even less light to reach us. Whereas during the summer, we're like down there. And so now we're getting that light more directly. So the idea is that during the summer, we could be like down here, but then during the winter, we would be up there as far as where we are on this tilt of the Earth. So that's why I meant that the solar intensity can vary based on the time of the year, roughly your latitude and things like that. So it's not always going to give you like a constant source of energy. And also, obviously, it has to be daytime in order for you to get solar energy. This is a map of the what we call the horizontal solar irradiance. This data is coming from the NREL, which is the National Renewable Energy Laboratory for the United States. So this is just giving you a little map of sort of the solar potential of various places across the United States. And so you'll notice the general trend is that the lower you are, the closer you are to the equator, the higher the solar potential is. And you'll notice that down here in the American Southwest, there's a tremendous amount of solar potential down there. And the main reason is because it's south and also the elevation is really high over there. And so the higher you are, like over here, the higher the elevation is, the less of that decrease you're going to see. So there are some elevation effects as well in this data. But you can see that Kansas is kind of right in the middle. Like we've got some places that are pretty high and we got some places that are pretty crap. But even still, it's not that much of a difference. Like if you look down at the legend down here, you're just looking at a difference of like 4 kilowatt hours per square meter per day versus 5.75. So it's not that much of a difference. Solar is going to be useful anywhere, but you're obviously going to get the maximum benefits if you live down in the American Southwest. What questions you guys have for me about all this crazy stuff I've talked about so far? We good? Cool. Let's do a calculation. Let's estimate the area of photovoltaic cells that we would need to provide 2.5 kilowatts of electric power. 2.5 kilowatts, you could say that's about like the typical household probably needs about that much at its peak. So like if you want to run your like your heater, your air conditioner, like your refrigerator, your television, all the different things in your house, I'd say like about 2.5 kilowatts is a pretty good amount of power that you want to give to an average house. So what area of solar panels would we need? We will assume about 20% efficiency. That's pretty low. We're being a little bit over cautious here in the calculation. Most solar panels are around 30%, but let's just go with 20. And then we'll go with the global average intensity. If you remember what that was, is 245 watts per square meter. And we're going to go with 20% efficient. All right, so let's calculate the amount of area that we'd need to get up to 2.5 kilowatts. Okay, so the first thing we know is that power is going to be found from the watts right there. So if our area was 1 square meter, then what would our power be? It would be 20% of 245. So this will give us the power per square meter. So we just have to do 0.25 times 245. So I'm grabbing my calculator. So zero point 0.2 times 245. So that's 49 watts. And we want to figure out, well, what area would we need to get to 2,500 kilowatts? So if each square meter is 49 watts, we can figure out how many square meters we would need by just dividing these two things. So the area that we would need would be 2,500 watts divided by 49 watts. And so that would give us 2,500 divided by 49. So that would give us 51 square meters. So if I take the square root of that, so the square root of 51 is about 7. So you would need a array of solar panels that are roughly 7 meters by 7 meters in order to power a house. And that seems doable. You could put that up on the roof, and then you probably meet all of your energy needs in ideal conditions, during the summer and during the daytime. So that's just an example calculation for solar power. So this is the key to everything, is how much energy is going to be radiated down. Now we did everything at the lowest end, like 245 is the global average. So there's places that are much higher than that, and there are places that are lower than that. We also assumed only a 20% efficiency. We still found an area that was quite reasonable. So you could power a home off solar power pretty easily. Now, what about like a airplane or a car? Well, if you want to power a car off of solar power, it's not going to work. You just won't be able to have enough area on the car in order to generate the power that you would need. And so, but for a house, it works. But you'll probably never ever see solar powered cars. Like, it just won't happen. You might see electric cars that you have a solar panel on the roof, but it won't be able to generate as much power as the car would use. So you'd have to probably like park the car and then let it charge up a little bit, and then you could drive it around. But you're never going to have a car that's just purely using solar power without any batteries to store up the energy. What questions do you guys have for me? Okay, I'm going a little bit slow, so maybe I can speed things up here. All right, let's talk about the Three Gorges Dam. This is one of the largest hydroelectric dams in the world. This is in China, and I just saw this article, and this is the link to it, but I just saw this headline and I thought it was awesome. Breathtaking force. World's most powerful dam opens in China as gushing water generates the same power as 15 nuclear reactors. So this thing is just ridiculous. Like, the flow rate out of this thing, so the water that's flying out of here right now is 70,000 cubic meters per second. 70,000 cubic meters of water per second. That's just a ridiculous amount of water coming out of there. Now, this dam is extremely tall. Like, this is really high. So at this perspective, it's kind of hard to kind of get a sense of scale. Here's another picture during the day of those jets of water coming flying out of there. this is a picture close up, so you can just see like this mass of water. So when you're looking at it over here, you're like, oh, there's just this little tiny bit of water coming out of here. But then we actually like get down to a human scale. Like look at the railing there. It's like you'd imagine like a person would maybe be like that big, and you just see like this huge mass of water just like shoo, like flying out of there. There's a lot of energy in that water, and so what we want to do is harness that energy and turn it into electricity. So we'll look at this as our mathematical model. So we'll say that we have some mass of water up here, and we're going to just let that mass of water fall through this distance h, and we'll take that gravitational potential energy and we'll convert it into electricity. Now, it's not going to be a perfect conversion, but generally these hydroelectric plants operate at around 90% efficiency. I think the Three Gorges Dam is like 93%. So it's pretty good. It's pretty good efficiency as far as we're concerned. If you remember, like coal was like 30%, solar panels usually about 30%, wind is like 30%, natural gas is like 60%. So 90% is pretty good. We like that a lot. All right, let's do some calculations. We're going to try to derive an equation that can let us calculate the power output of a hydroelectric dam like this. So the mass of water m falls a vertical distance h. That's our setup. And so what we want to do is figure out, well, what is the mass of water? Well, because if you look up here, we're given the flow rate in cubic meters per second. So we want to figure out, we're not going to have kilograms of water. We're going to have like an amount of water flowing per second. We're going to have like a flow rate of water. So what we want to do is we want to convert that mass of the water in terms of the volume of the water. And so the way that's going to work is just by using the equation that mass is the density times the volume. That's just from the density, volume, and mass relationship. So the mass of the water is going to be the density of water times the volume of the water. And so realize that the volume, like realize that this thing up here is actually a cube of water. So it's a cube of water, like a volume of water that's going to be falling down. So what is the potential energy of the water? Well, potential energy is just mgh. And so now we're going to use, for the mass of the water, we're going to use that rho v gh. And so that's the potential energy that the water has. It's going to be the density of water times the volume of water times the gravitational acceleration times the height of the dam, or the height that the water has fallen. So now we want to find an expression for the power output. So finding the power output is simply power is equal to energy divided by time. We have the energy, which is just rho v gh divided by the time. And so usually this is represented as a delta V, like an amount of water, but I just left it as a V just for whatever reason. But generally it's like they'll say like it's a quantity of water, delta V. What we do is we take this term V over T, which is basically the volume of water that flows over time, and we're just going to call that Q. And this is called the flow rate. The unit of the flow rate are units of volume divided by units of time. So the unit is meters cubed per second. And so that'll be the flow rate. So when we write out our equation for the power of a dam, we say power equals rho Q. So the density of water times the flow rate times G times H. And the density of water, if you guys don't know it, the density of water is 1,000 kilograms per cubic meter, which works out to being one liter is 1 kilogram. 1 kilogram per liter. Let me write it like that. 1 kilogram per liter. So if you have a 2-liter bottle that you usually buy at the store with soda in it, and you instead fill it with water, it'll be about 2 kilograms. So it's a kilogram per liter. All right, here's some data that I grabbed off Wikipedia for the Three Gorges Dam. On the left, we have the flow rate at the dam site. So this is going to be giving us our Q value. And then over here is the power output. And so you notice that the flow rate, it's the Yangtze River. I'm probably pronouncing that wrong, but the Yangtze River. So that is the river that feeds into the dam, or the dam is blocking that river. And you can see that the flow rate is going to vary throughout the year. Well, obviously, based on like snowfall, when it melts, the different time of the year, you're going to have different flowing rates of water flowing through the river. And so you notice that at its peak, the flow rate is about 30,000. So that's at the peak. The flow rate is 30,000 cubic meters per second. And then when you're at that peak flow rate, we'll notice that you actually can reach up here a maximum possible power output, we're looking at the blue line of 22,500 megawatts. And so from this data, I thought it would be interesting to estimate the height that the water falls. So determine the vertical distance h through which the water in the Three Gorges Dam falls. So we just determined was that the Q, the flow rate of this dam is 30,000 cubic meters per second, and the power output of the dam is 22,500 megawatts. So now you can see why they're talking about this being 15 nuclear reactors, because 22,500 megawatts, it's 22 and a half gigawatts of power. That's a ridiculous amount of energy coming out of this dam. But realize that that's under ideal conditions, right? That's when you have this maximum flow rate and all the generators are turned on and everything is perfect. These are the ideal conditions. So it's not going to be doing this 24 hours a day year round. All right, so if we look back to the equation, our equation was power is rho Q GH. So the density of water times the flow rate times gravitational acceleration times the height. And we're trying to find the height. So if we rearrange this equation to solve for height, the height of the dam is going to be the power output divided by rho QG. So the power output is 22,500. These are megawatts, so we have to raise it to the sixth power. The density of water is just 10 to the third power. The flow rate was 3 times 10 to the 4. And then G, we'll just call that 9.8. And so if we throw all this in a calculator, I'll do it real quick. I'm not using my calculator on screen because I've been having issues with it lagging out the video, so I don't want to do that. So I'm just going to use my phone to calculate this. If you have a phone or a calculator, you should try to do it along with me and see if you can get the same answer as me. Let's see, so 10 to the third. So I'm taking 22,500 times 10 to the sixth divided by 1,000 times 3 to the fourth power times 9.8. I got 76.5 meters.
I also did.
Awesome. If we look at our data up here, it looks like we could probably just find maybe like 2 sig figs here. So we'll just say that the height is approximately, that's a disgusting approximate sign. The height is approximately 77 meters, or you could say 80 meters. And I looked it up, and that's actually exactly right. It's actually a little bit higher than that, but obviously it would need to be higher because this is theoretical. We're assuming no energy loss. So if you actually calculate at 90% efficiency, you end up getting the height is about like 86 or so meters is what it ends up working out to. So that's cool. So we did it. So that's 77 meters is pretty big. Remember the real number is about 80 meters, but you can see why like that's just a really tall distance. This water is just shooting out of there. Like this is a really tall dam. So the water is falling from, but behind the dam back here, you've got a water level like this, and then that water is shooting out to this lower level, shooting out of the dam like that down to the lower level. And so the water is falling. So if this is the dam up here, the water is falling that there's your H. That's the distance that the water is falling. And the generators aren't going to be like down here. The generators are probably inside there. So the water is not really falling all the way down there. Like we're only harnessing this, the distance from the top of the water level down to the generators. That's hydroelectric power. Okay, I'm doing on time. I got 6.5 minutes left. Oh my gosh, I'm taking forever. Okay, let's talk about wind power. So wind power converts kinetic energy of the wind into electrical energy. And we've seen these all over the place because Kansas is a hotspot for wind power in the United States. What we don't really see too much in this country, which is a lot more prevalent in European countries, are wind farms or windmill farms. This is an offshore farm. This is the London array. Just to give you some stats on this is just a huge array. They have 175 turbines in this array. It costs $1.8 billion to build this. It generates 650 megawatts. So 650 megawatts. Remember the Three Gorges Dam was 22,500 megawatts. So this is a fraction of that. But realize that this is also way cheaper. The Three Gorges Dam was like a major, massive engineering project. The height of the hub, which is how tall the wind turbine is, so that's up from the ground up to the hub. The hub height of these turbines is 87 meters. That's really tall. 87 meters is a lot taller than you think. The whole area of this site is 122 square kilometers. The blades on these turbines, like one of the things that we don't really think about is how huge these blades are. They're massive. So I just want to show you guys a picture. The blades are 36 meters long. So there's like half a football field. These things are enormous, just massive. I just want to show you some pictures of like trucks and stuff carrying these things around. Because when you see them like mounted up 86 meters up in the sky, they don't look that big, but they're actually enormous. They're just massive, massive turbines. Maybe you guys have seen these blades. Like I remember driving on road trips, like seeing one before, and I'm just like, oh my god, like the thing is just huge. It's ridiculous. Like you can see the person right there compared to this blade, and then realize that there's not just one of those blades. There's three of them on here. These things are massive. They're huge. All right, so what we want to do is we want to determine an equation that can calculate the theoretical power output from a wind turbine. So what we're going to do is we're going to consider a mass of air m that can pass through a tube of cross-sectional area A with velocity v. So realize that the wind's going to be flowing in here like this towards the windmill, but realize that if the wind is too low, it's going to miss the blades, and if it's too high, it's going to miss. So really what we want is this tube. Now realize that it is a tube because they're spinning around in this circle. And so this is the tube that the air is going to hit. So we'll call this the cross-sectional area. We'll call that A. So that's just the area that the turbines are going to sweep out. We'll call it A. The wind is going to be moving at a speed V. And then we'll say that the time is delta T. So we'll say that like the length of this tube from here to here, let's say it takes a time of delta T to travel the length of this tube. So that means that the length of this tube is V delta T. So distance equals velocity times time. So if the wind speed is v, then it'll take time delta t to travel this distance. So that means the distance is v delta t. So we've basically got this cylinder. Here it is. The cylinder, the volume of the cylinder is calculatable. So what we want to do now is calculate the length of the tube. And we just said the length of the tube was v delta t. And now what's the mass of the air that's in that tube? The mass of the air is the density of air times the volume of the air. So just like before with flowing water, this time we have flowing air. So we're going to say it's the density times the volume. Well, we know what the volume of the tube is because the volume of a tube is the area, the volume of a cylinder, rather. So if you have a cylinder like this, the volume of the cylinder is the area times the length. And so we know what the area is, it's V delta T. And so the volume is going to be V delta T times area times A. So that's the mass. So the mass of the air is this crazy expression over here. And so realize that all of this stuff, this whole piece here, that's just the volume of the air in that tube. And so we're saying that as this air flows, you're going to see like a certain amount of air that's going to hit the turbine. And what we want to do is calculate the kinetic energy of all that air and then spit it into the power equation. So determine an expression for the kinetic energy of the air. Well, we know how to find kinetic energy. It's 1/2 mv squared. So we know what the mass is. It's rho. Rho, this is a Greek letter rho, by the way. That's the density. So it's rho times area times v. I should have made clear that that's the velocity of the air. That's not a lot of times people on the volume, they'll put like, like lines like that, like serifs to like show that it's different than the v. So that's the speed. So we got rho times area times speed times delta t times v squared. So you notice that there's actually a cubic here. So there's a V inside the volume, and then there's also a V inside kinetic energy. So the power actually is going to go like a cubic of the velocity. It's going to go like the velocity cubed, which is pretty crazy. All right, so now we want to calculate the power output. So power is energy over time. So it's just like with the dam. We have the energy. It's 1/2 rho A V delta T. Whoops. So delta T V cubed divided by T, and we'll realize that that's just a certain amount of time. So if we say that that time is a second, then these would cancel out, and then we'd get that the power of a wind turbine, the power output of a wind turbine is this ridiculous equation. So it's 1/2 times the density of the air times the area swept out by the blades times the velocity cubed. All right, now this is a theoretical model. This is not at all going to be realistic. We'll talk about the limitations over here in a second. But for now, just looking at this relationship, what happens if we double the area? So if you double the area, what will that do to the power? So if you just look at this area here, if we multiply the area by 2, what effect will that have on the power?
double it?
You got it. It would double the power. So if we make our blades sweep out twice as much area, we'll get twice as much power. And what about if we double the wind speed? So what if it's a really like windy day and the velocity of the wind is doubled? So what if this velocity here gets doubled? So what would be happening is you'd be doubling something that's getting cubed. So doubling the speed would actually end up giving us
8 times that value.
8 times as much power. So that's pretty intense. Like if the wind is blowing twice as fast, you're going to get 8 times as much power. The problem though is like you don't want wind turbine blades to be going too fast because they could actually like overload and like blow up. Like and then also they're really noisy, and the faster they move, the more noisy they are, and so people that live around them can get kind of upset about that. All right, so what are some limitations of this model? My time just expired, so I'm just going to quickly finish this up. So the limitations of the model are number one, we were assuming all kinetic energy is absorbed, is transformed, or let's say transferred. And so what that would mean is that if the air was coming in at speed v, what would happen on the other side of the turbine? That would mean that the v would go to 0. And that's not realistic. The air isn't just going to stop flowing on the other side of the turbine. So this model was neglecting that. So we're going to get a bad answer from that. What are the other limitations of this model? It's ignoring the efficiency, like energy losses. So it ignores energy losses. So this is just a theoretical, put it like an asterisk next to it. This is a theoretical maximum. You're never going to realize this in real life. Here's a Sankey diagram of a wind turbine. So you can see that there are turbulence effects that cause you to lose energy. There's friction in turning the turbine. And then there's energy losses to the grid. And then when all is said and done, you only end up capturing about 30% of the energy that the wind is delivering. There's also the wake effect. I just want to mention this because I think it's really fascinating. If the wind is coming in at a bad angle, you can see that the wake or the turbulence created by that first turbine, all the other turbines can be in the wake, and that will drastically decrease the subsequent wind speed that the other turbines see, and it'll really reduce the output of your array. So you generally want to try to space these turbines out like in a staggered approach. So like if one turbine is here and one turbine is here, you wouldn't want to put the next row right behind it. You wouldn't want to do that. You'd want to put it in the middle. So that way when the wake comes out like this, you can generally try to avoid those wake effects. So there's a lot of thought that goes into designing those windmill farms and stuff like that, but there it is. And then I'll end with this map. This is a cool map showing you the wind resources of the United States. And you'll notice the key things to notice here are the coasts are highly useful for wind energy. Also, this is 80 meters above surface level, which is where you've got, when you have the wind turbine with the blades coming out like this, the hub of that turbine is about 80 meters up. And so um, that's why I was looking at the wind speed 80 meters up. So offshore potential is very high. And then also you'll notice that where we live in the center of the country, we have these really high values up here. So we're able to get a much higher wind speeds up here. And so remember that if you go from this lowest end where it's 3 up to 6, that's 8 times more energy. And then if you go from 3 up to 9, that's 16 times more, right? Wait, no, that's another factor up from there. Anyway, I think it's times 6. I don't know, whatever. But the point is that like we generate a lot. This is one of the reasons why Kansas is able to generate 60% of our electricity mix is from wind, because we're in a really good spot for wind here in Kansas. Okay, that's it. If you guys have any other questions, let me know now, and then I'll shut off the video. I guess we're good. All right, have a great day, everybody. Talk to you later.